quantitative calculations with gas laws are a piece of cake. It's usually plug and chug. You can often see if your final answer is reasonable. The kinetic molecular theory is used to really describe qualitative aspects of gas behavior. These are good theories or good postulates. Let's look at each one. Gases are made up of particles with no defined volume, but with a defined mass. In other words, their volume is minuscule or insignificant compared to the distance between themselves and other molecules. Sometimes I'll have an issue with this saying, gas particles have no defined volume. I mean, isn't that a property of matter? All matter has mass and volume? But here's what they're referring to. That in a sample of gas, the particles themselves are really far apart, and the gas particles themselves are ridiculously tiny. So, I mean, I might have a balloon, and I could have a sample of gas particles in that balloon, but they are so small that there's a very significant distance between the gas particles. If you were to condense all of those gas particles in a balloon, as small as you possibly could, the volume would be insignificant. The volume of the gas particles themselves would be so small because that balloon really doesn't have that many particles, and they're so tiny and so far apart. That's what they kind of mean here by gas particles have no defined volume. They do have a defined mass, which we said can affect the density of the balloon or whatever the container is. The volume of the particles themselves is insignificant because they're so small and they're really far apart from one another. Gas particles undergo no intermolecular attractions or repulsions. We're going to imply that the particles possess no potential energy, and thus their total energy is simply equal to their kinetic energy, which would be related to their temperature. So we're going to assume that because these gas particles are so far apart, and they're obviously so tiny, any kind of intermolecular force is relatively insignificant. And along the same lines, if I had polar molecules, if they butt up to each other like partial negative to partial negative, we're going to say similar, that there really is no significant repulsive force because these gas particles are just so far apart from each other that any kind of intermolecular attractions or repulsions are insignificant. I'm fine with number 3. Gas particles are in constant or continuous random motion. It's impossible to predict the trajectory of a moving gas particle. All we can say is that they are constantly moving, and their motion is random. Number 4 says that collisions between gas particles are completely elastic. In other words, there's no net gain or loss of kinetic energy when particles collide. So it's almost like Newton's laws. These gas particles come together, they collide with a certain force, but they bounce off of each other with an equal and opposite force. That's kind of what we are referring to by saying that collisions are elastic. And collisions do not occur because of any kind of attraction between particles. If gas particles collide, it's because of their random motion. By chance, these gas particles were in the same place at the same time, boom, collision. But do they care? Not one bit. They collide and go off on their merry way. No change in energy, no transfer of energy. Completely elastic collisions. And finally, this 5th statement. The average kinetic energy is the same for all gases at a given temperature, regardless of the identity of the gas. Well, it's kind of the definition of temperature. Temperature is a measure of average kinetic energy. On average, How fast are those particles moving? This kinetic energy is proportional to the absolute or Kelvin temperature. So in other words, as I increase the temperature, I should increase kinetic energy. If I wanted to do calculations, temperature would need to be in Kelvin. Now look at this graph here. Here's a distribution of different samples of particles at different temperatures. We're looking at the velocity of the moving particles, the speed, meters per second, versus relative of number of particles, and this is nitrogen, it really could be anything. Number of particles with that given velocity. So here's kind of the deal. You might have a sample of, it could be nitrogen, it could be a sample of water. You throw in a thermometer. The thermometer is going to give you one temperature reading. That temperature is the average. On average, how much kinetic energy do these particles have? But that average kinetic energy that's measured on your thermometer, that should be the energy of most particles. So the highest number of particles would have that amount of kinetic energy. Or in this case, we're measuring velocity, so they're moving about the same speed, as long as they're all the same particle in our sample. As I increase the temperature, I'm making these particles move faster. And look kind of what happens, that this distribution changes just a little bit. That you seem to get kind of a larger sampling of particles. Now again, your thermometer is going to tell you the average kinetic energy. But there's always going to be some particles with more and some particles with less. Think of it as like I'm giving a test. I'm giving a test to 10 students. Well, the average score is probably the score of the majority of the students. I have a small sample. As I increase the sample, or here I'm increasing the temperature, there's a wider array of velocities. You're not going to know that on your thermometer. The thermometer is just going to give you the average temperature. It's like saying now I give a test and I'm looking at the distribution of 1,000 scores. Now the average score is still probably the score of the majority of students. So my thermometer is going to read this average temperature. It's still the temperature of the most particles. The majority of the particles will have that much energy. But now I have more particles with a little bit greater energy. And I have more particles in my sample that have a little bit less than average. We're not going to know that because the thermometer reading temperature just gives us the average kinetic energy. But when we get into the next chapter, we're going to look at something called activation energy. Energy required to get a reaction started. Well, often, like especially with solutions, like double replacements or something like that, you mix things together, bingo, you form a precipitate. And it really doesn't seem like you needed to add energy. You didn't need to heat it or add a spark. It didn't seem like I needed a significant energy source to start the reaction. Well, often that energy can come from the particles themselves. Certain reactions are very temperature sensitive, where maybe in order to get this reaction to occur, I'll show you one in the next chapter, the temperature needs to be approximately 80 degrees. Well, sometimes this reaction will go when the temperature is not quite 80 degrees, because my thermometer is reading the average temperature. There's always a small fraction of particles with more energy than the average. And there's always a small fraction of particles with less energy than average. But sometimes those particles with more energy than the average, they may have enough energy to already start the reaction. So we should kind of be aware of that. With temperature, it's average kinetic energy. There are always a sample of particles with more and a sample of particles with less energy, but we won't know that by looking at a thermometer. Now, again, throughout this study guide, we've kind of used the word ideal gas. Ideal gases are just gases that follow all these laws perfectly. They follow Boyle's law, Charles' law. They follow the ideal gas law, Hertner. They follow all the postulates of the kinetic molecular theory. You know, if I do a calculation for volume, I go in the lab and that's exactly what I experience in the lab. Real gases should follow all of those laws in reference to pressure and volume, temperature, and number of particles. But that's a little different than what we might really experience in the lab. Often we do gases, or labs with gases, and you might think, the data's not quite what I expected, but that might just be due to the nature of the particle. For example, real gases might have some relatively significant intermolecular forces. Now obviously they're still in the gas phase, so the intermolecular forces are weak. But what if I change the conditions a little bit so that the temperature is low? What if I'm at a low temperature and those particles have less kinetic energy, less energy of movement? And so maybe they're not moving as fast, maybe they're not colliding as often or colliding as forcefully. And as I continue to decrease the temperature, we could eventually start to get to a point where we're ready to condense the vapors. As I continue to decrease the temperature to that boiling point, the temperature where now I would condense the vapors, I'm bringing the particles closer to each other. As I bring those gas particles closer to each other, now intermolecular forces might be significant. I mean, there's always intermolecular forces present. Can be present. Well, they're always there, but they're just not very important because often the gas particles are bouncing all over the place. They're really far apart. But at low temperatures, as I get to the point where I may condense the vapors, those particles are starting to come closer to each other. As I bring those gas particles closer to each other, now intermolecular forces might be significant. So we say that gases behave more ideal at high temperatures. We want to keep the particles away from each other. And when I think about a gas, I think of particles that have lots of energy, they're bouncing all over the place. They're not close to each other. So one way to do that, to keep the particles away from each other, is to keep the temperature up at high temperatures. Because then intermolecular forces will not be significant. This other option, at high pressures. Think about what happens at a higher pressure. As you increase the pressure, we decrease the volume. So here I'm increasing the pressure and decreasing the volume. Well, what if I increase the pressure so much to the point that those particles are forced into a very small volume? They're very close together now. Well, now the volume of the gas particles themselves might be significant. The volume might change a little bit because I'm smushing those particles so close together. Usually, the volume of the container is equal to the volume of the gas particles. And the particles themselves really don't contribute significant volume, so we never really include it when for calculating volume. But if I have high pressure and a really small volume, the volume of the container might be a little different because the volume of the gas particles themselves is more significant. There's also the chance of intermolecular forces taking over too. If I'm pushing those particles into a small space close to each other, now their volume becomes more significant, the volume of the particles themselves. And those intermolecular forces again could start to even more bring the particles close to each other. So again, we want to keep the particles away from each other. That's when gases behave most like those statements in the kinetic molecular theory. So we're going to try to keep the pressure low. Under low pressures, the particles should be far away from each other. Notice kind of the key to gases behaving ideal. Large volumes. We could add that in there too. In a large volume, I'm going to keep the gas particles far from each other so that the volume of the particles themselves is insignificant because there's so much space in between the particles. Most of the volume in the container is just blank space, air. And if the particles are far from each other, intermolecular forces are insignificant. So again, they might give you a question that would say like A, B, C, D. Under which of the following conditions will gas particles behave most ideal? Think about getting those suckers far apart from each other. High temperatures, large volumes, low pressures. Another kind of question they might say, A, B, C, D, which of the following gases would behave the most ideal? Non-polar gas molecules. Non-polar molecules behave most ideal. Do you see why? I bet you have a guess. Intermolecular forces. The intermolecular forces are going to be the weakest between non-polar molecules. You know, if I have water vapor or ammonia gas, will I have stronger intermolecular forces? Now, if I have some kind of conditions where the particles become close to each other, those intermolecular forces could be significant. I'll see less pressure than what I might expect, and the volume of the gas particles themselves may be significant. So those are two kinds of questions that you might see on the AP test, probably like a multiple choice style. I would remember the conditions required for gases to be most ideal. Weak intermolecular forces, large volumes, high temperatures, and low pressures.